How's everyone doing?
Pretty good.
Awesome.
Good day.
Good, glad to hear it. All right, so I want to go over the homework that you turned in yesterday, and I have not gotten that graded and loaded in Canvas. But I want to talk about it today anyway, because some of this stuff might be related to the midterm. And then I want to talk about the midterm, just kind of give you an overview. I posted a topic summary yesterday to Canvas, and I also posted your next homework. So if you have questions on that, we can talk about that. But mostly we're going to spend today just doing more work with state machines, doing analysis of state machines. So the same things we were doing on Tuesday. This time, hopefully, the entire audio ends up on the recording. So I'll try to keep an eye on it this week. I happened to be playing with a proto board a couple of days ago and had a mishap and had to toss this one, but in the process it fell apart. And so if you're curious about these things, right, these are the boards you use in Tinkercad. You'll use them in the actual lab when we're back in person. But you know, you put wires in here and it makes connections. This is what's going on inside, right? So this is the underside of it, and you can see the wiring really clearly when you look at it like this, right? And each of these areas has just a little connector like this sitting in there, and it's pretty hard to see, but it's just a pressure fit, right? So it's a pair of plates of metal that will sit inside here and accept a wire when you put it in. And then these power rails on the top, that's just a gang of these things all connected together. And those go in here, and that, you know, establishes the connection that anything plugged into this row of holes will be electrically connected. And that's really all there is to it. It's just a shortcut tool for wiring circuits together. And we call these proto boards, but they're also called breadboards, and that's the name that I sort of grew up associating with this. And they're breadboards because they used to be made on breadboards, right? So you would get a piece of wood and you'd hammer nails into it, and you could wrap wires around there, and you could solder them if you were serious, but you could usually just wrap them around and get pretty good contact, and you could build circuits like that, right? And then you could change them by just, you know, physically unwrapping this resistor and moving it somewhere else, and so on and so forth. So that's what you're saved from having to do by, you know, having these versions instead. All right, so any questions before we just kind of go through the homework? All right, so question one was this circuit, and I mentioned that, you know, the goal here was really to explore the circuit, see what kinds of things it can do, and then when you have sort of seen the different behaviors it can exhibit, to draw a timing diagram to illustrate what you learned. So if you think about this circuit, right, it's got two inputs, S and R, and it's got an output Y. And we can just start filling in ones and zeros, but since this has feedback, right, its behavior is more complex than just what are the inputs, here's the output. It's going to have a memory of some sort. So if we think about an OR gate, one thing about an OR gate is as soon as an input is 1, the output is fixed. Right? If we make an input 1, we know what the output's going to be. It doesn't matter what the other input is. And so in what case do we have a 1 going in on this input? Well, that's the case where R is a 0. So if R is a 0, it doesn't matter what S is. the output of this inverter will be a 1. A 1 going into an OR gate will make the output a 1. Since this is a NOR, the output will be a 0. And that's guaranteed. Doesn't matter what happened in the past, doesn't matter what S is, doesn't matter what the previous value of Y was. 0 in here puts a 1 there, 1 into an OR gate, 0 comes out of the NOR. So then the other questions are, what happens if R is a 1? Well, if R is a 1, then the output of the inverter is a 0. And a 0 going into an OR gate has no effect on it. And so if R is a 1, we could actually redraw this circuit to look something like this. Here's S. Here's an AND gate. And this is now a NOR gate with a 0 going in. Well, if you have a NOR gate and one input is a 0, what is that gate acting like? Could we replace that with a different gate?
Couldn't it be an inverter?
It's just an inverter, exactly. Because if you have A, B, and the NOR, right? If A and B are both 0, this is a 1. If any of them is a 1, this will be a 0. So that's our NOR gate. Well, if we know that say our B input is a 0, then we only care about these two rows. And in each case, you know, this 1 is the opposite of A, this 0 is the opposite of A. We can see this algebraically also. This is just saying A or 0 inverted. In other words, the NOR of A and 0. Well, A or 0 is just A, so it's just A bar. All of which tells us that this NOR gate is really acting like an inverter. So in the case where R is 1, this is the same circuit. Alright, well, if S is a 0, what's the output of the AND gate going to be?
A 1.
So 0 right here going into an AND. What's the output of the AND going to be?
Sorry, it's going to be a 0.
Yeah, the output of the AND is a 0, and the inversion gives you a 1. So if S is a 0, doesn't matter what the previous value of Y was, right? We know that a 0 going in, Y is going to be a 1 coming out. You can tell I'm getting ready to make banana bread because I have these little fruit flies running around now, which means my bananas are ready. All right, so these are combinational. These have nothing to do with the present or the previous state, right? These are guaranteed. The one state that's still left is if R is a 1 and S is a 1. Well, if you put a 1 into an AND gate, what can we replace that AND gate with? So I have an AND gate, one input is a 1, the other input, let's just call it A. What can we say about that output value?
It's determined by A.
Yeah, it's exactly equal to A. So this is really just a wire. So in the case where S is 1 and R is 1, our circuit really looks like this. And it's that first circuit we played with a week ago where we just had an inverter feeding itself. And so in this case, Y is going to be oscillating. Alright, so this is our informal analysis of the circuit. But now if you want to make a timing diagram to describe this, we could do something like this. So let's imagine an input S and an input R, and let's show Y. So first I want to illustrate that if R is 0, so I'm going to put a little dotted line here just to show, you know, R is a 0. And I don't care what S is, so I'm going to show S going up and down and up and down. And I'm going to show that y is a 0. And I'm going to put this dotted line in the beginning so that we know this is low as opposed to high. So this part of my diagram is illustrating something really important. If r is 0, s has no effect, and the output is 0. And now I'm going to leave s at 0, and I'm going to set r up to 1, and our output's going to go high. So that's the 0, 1. And I'm just going to leave s low for a bit, and I'm going to let r drop low and go high and drop low. And I'm going to show that y is following that r value. And now I'm going to raise s again, which has no effect because r is a 0. But now I'm going to raise r at the same time so that both s and r are high. And at this point, y is going to start to oscillate. And then at some point, maybe I'll drop s. And so now s is 0, r is 1. That's going to leave y high. And that probably describes, every possible situation that can change the behavior of this circuit. So this is a key part, right? The idea that there is a combination of inputs for which just leaving the circuit alone, the output's going to bounce back and forth, right? And that's unusual for combinational circuits, but a circuit with feedback, that happens in this case. So that's one thing to note. So I saw some people where they had a trace for y and another one for next y, which we don't have to do. We can show the full behavior of y on a single trace because remember, our horizontal axis represents time. So this is basically saying, if the present value of y is 0, a little bit later it's going to be a 1, a little bit later it'll be a 0, and then a 1, and so on. So we can capture that time behavior of a signal by just drawing it horizontally. So that's the main idea of timing diagrams, right? To capture the way that inputs or outputs change across time. All right, question 3. So any questions about that? So question 3, we were asked to draw a clock signal and an excitation input signal to load in the sequence 10110, paying attention to setup and hold times. And this was for a clock with a 0 to 1 timing event. So we have a clock signal, it's going up, it's going down, it does that forever. When it changes from 0 to 1, that's when the clock is triggering. That's when our flip-flops are going to change, potentially. So let's draw a picture similar to this, where we have a clock. And here's excitation input, so EI. And the triggering happens on the rising edge, so it's going to be these points right here. Non-zero setup time, T setup, non-zero hold time, TH. And we want to input the sequence 10110. So when this clock ticks, the input has to be high. And the setup and hold time business just says we can't change the input right when the clock's ticking. It's got to be held for at least a little bit of time before, and it's got to be stable for a little bit of time after. And depending on what those setup and hold times are, we could draw a bit of a window around here. Like that. And we could shade that in if we wanted. And it's saying during this window, the input isn't allowed to change. So if you want it to be a 1 right here, it's got to be a 1 before you get to this time window. And then our next input value is a 0, so it's got to go low at some point, and it can go low anytime as long as it's a little bit before the clock tick. And then we want to input a 110, so I'll raise it up here, and I'll leave it up there, and then I'll drop it down to a 0. And we have these time bands around each clock tick. And the important thing is the input's not changing during those time bands. So that's a good timing diagram for this system. Now, sometimes, you know, when you actually build a system like this, what you do is you would say when the clock is low, when it drops, that's when we would change the inputs. So the input changes would happen shortly after this falling edge. And as long as your clock is slow enough, there's enough time for everything to settle so that these are totally stable by the time you get to the next rising edge. And so when the clock is low, that would be your time to, you know, adjust the excitation input. And then when the clock goes high, that's when it gets loaded in and so on. All right, question 4 was that funny one about making an XOR gate, making a toggle gate out of a D. So we've got a D flip-flop. And we want this to act like a toggle. Turns out this is actually in the textbook. If you look at the section on T flip-flops, they actually have a picture of a circuit that will do this from a D flip-flop. So D flip-flops look like this. Clock ticks. If your D is a 0, your output's a 0. If your input's a 1, your output becomes a 1. Toggle flip-flops have this behavior where if your toggle input is 0, your output doesn't change, but if your toggle input is 1, your next value of Q is the opposite of your current value. And so the idea is, let's take this and feed it into some block of combinational logic along with a T input to generate the right D value to do this kind of thing. And so what should this combinational logic do? Well, if T is a 0, and let's just call this, you know, X and Y. If T is equal to 0, we want our output Q to be unchanged, which means the value we want to send in to D should be whatever the current value is coming out of Q. So if we were to simply take Q and feed it back into D, then when we tick the clock, nothing changes. Because what's the new value? Well, it's the same as the old. So if T is 0, we want this output Y to be equal to whatever the input is, X. But if T is 1, we want our flip-flop to change value. Which means if this is a 1, we want our D input to be a 0. And if this is a 0, we want our D input to be a 1. So if we just think of this combinational logic block, we want Y to be the opposite of whatever the input X is. So if we can build a circuit that does this, we can plug that in right here, and we can make ourselves a T flip-flop. Well, how do we build a circuit? Let's make a truth table. So this block of combinational logic has two inputs, T and X. It has one output, Y. So let's make its truth table. If T is 0, Y should just equal X. So that should be a 0, 1. If T is 1, Y should be the opposite of X. X is 0, 1, Y should be 1, 0. there's our truth table. We can write y. It's just a sum of two min terms. So it's t bar x or tx bar. And there's a special name for this function. So what's this function?
XOR?
That's an XOR. So that's why if you take a D flip-flop, bring the output back around and XOR it with T, this whole thing acts like a T flip-flop now. All right, and then question 5, this is another exercise in working with timing diagrams. So again, time is moving horizontally. And we've got the table that describes what an SR flip-flop does. And so this is a negative edge triggered SR flip-flop. So on these falling edges, the output's going to change according to the values of S and R. So it's really just filling in the blanks here. So S is a 1, R is a 1. When the clock ticks, that tells us Q should become a 0. So at this point, Q becomes a 0. And if you're doing propagation delays, this will happen a little bit after the clock tick. At this point, S is a 0 and a 1, so let me just write these in. So this is a 1 and a 1. This is a 1 and a 0. 1, 1. 0, 0. 1, 1. And 1, 0. So 0, 1, the output should be a 0. And that'll go until we get here. 1, 1, the output should be a 0. And then 1, 0, the output should go to a 1. So after this event, it's going to rise. And then 1, 1, it should go back down to a 0. 0, 0, it should stay whatever it was, which will be a 0, 0. 1, 1, it stays a 0. And then 1, 0, it should rise to a 1. So you get an output trace, something like that.
What if it was 0 from the start all the way up to that first bar?
So if it was 0 here, we've got a 0, 0 coming in. So then it would be low. And it would stay low all the way out to here.
Ah.
So if you took that to be a 0, that's fine. But mainly there's a bump here and then there's a uptick here. Those are the ones I'm looking for. And if I wanted to say that this was a 1 in the beginning, usually when I drew it, I would put a little dotted line here to let you know this is high, right? If I wanted it to be low, I'd put a little dotted line going down to it, or you could label it, you know, as a 1 or something like that. So that's potentially ambiguous in the beginning. Another thing you'll see in timing diagrams sometimes is something like this, where you might see something high and low, and a lot of times these are done with an X in the middle. That means we don't know, right? It's an unknown level. It could be high, it could be low. And there's some circuits where in some conditions we can't tell if the input's high or not. And so you'll see a mark like that. And timing diagrams are probably your most common tool when you work with circuitry. So I'm working with a chip on a pet project right now. It's a digital to analog converter, and this is what you're given in the data sheet to tell you how to hook this up, right? So here's a signal which is going to drop from high to low. And here's another signal that I'm going to drop from high to low. And then sometime after that, I'm going to drop this signal from high to low. And here's some output signals, and they could be high or low. But during this period of time, those signals are guaranteed to be stable. And you need to have certain timing constraints. For example, when I raise this signal, right, I have to wait a certain amount of time before I raise this signal. That's called T sub H parentheses CS chip select. Here's TH DAC, here's THD. And elsewhere in your data sheet, you'll see numbers for all of these times. And you'll usually see a minimum or a maximum based on the timing requirements. So this is something that you'll definitely encounter anytime you work with physical components. And sometimes you encounter them in software, right? If you're writing a device driver and you're interacting with something, you may have to know what the timing characteristics are of a system you're working with. And it's usually done in the view of timing diagrams. And real timing diagrams, you know, they usually draw these at an angle to acknowledge the fact that our signals don't change, you know, like a knife edge. That's physically impossible. It's actually a small drop or a rise in voltage level. So those you'll definitely encounter, and they're good to get comfortable with, and they just capture information that you can't really capture in a truth table.
Race conditions are the worst to try and debug.
And race conditions are the worst. And race conditions, so this is highly topical. Race conditions come in the following situation. Let's suppose we have an OR gate. And here's an input A, and here's an input B, and an output Z. And suppose A equals 0, B equals 1, and now something's going to change, and A is going to become a 1, and B is going to become a 0. And so, you know, in this case, Z is a 1, in this case, Z is also a 1. But if we look at the timing diagrams for this, right, so A is a 0, B is a 1, and then A changes to a 1, B changes to a 0. So here Z is high, but there might be, you know, a brief period between the time that B has changed to a 0 and A has changed to a 1. And during that time, our output could go low. Well, if you have a flip-flop with an output which says, you know, system okay, and it's got this, you know, asynchronous clear input, and you've got Z connected to this, and, you know, if your inputs are 0, 1, everything's good. If your inputs are 1, 0, everything's good. But if B drops before A rises to a 1, and this Z output goes low temporarily, what's going to happen to your system OK signal? Well, when it sees the low input on clear, it's going to go low. And it's going to stay low, unless something causes it to change high. So this little glitch, which came up because of this race condition, this question of which signal is going to get to my OR gate first, created a glitch, and that glitch can cause a permanent change in the state of my system. And so that's why we're building systems with clocks, so that we can basically say, I know that things are going to happen, things are going to go through intermediate values that are invalid and so on. I'm not going to pay attention to that until the next clock tick. And so in our state machine, right, the clock will tick, and then we'll look at all the inputs, we'll update all the flip-flops, we'll go through the combinational logic and so on. And so it's an attempt to sort of like ignore the world while these things are happening. Now in practice, you know, we're building a system with 500 million transistors, you know, a few 100 million gates. We can't analyze that ourselves and know, you know, is there a situation where this is happening, right? So we have software that does that for us. And one of the longest parts of having this software work on your design is doing the timing analysis. And it will look for things like this, critical race conditions. It will also do things like, what's the longest time it's going to take from a change in an input to a change in an output? And depending on your circuit, that answer may not be obvious. So here's a circuit that it's kind of silly, right? It's got 4 gates in it, and if each one of these has a 10 nanosecond delay, my total propagation delay from input to output is going to be 40 nanoseconds. All right, here's another system with 4 gates in it. Each of these have a 10 nanosecond delay. Let's suppose the NAND gate is also 10 nanoseconds. My maximum possible propagation delay from input to output is only 20 nanoseconds. Because the 10 nanoseconds when this thing is settling, this thing is also settling, this is also settling. So after 10 nanoseconds, all of my inputs to my AND gate have been stabilized. Another 10 nanoseconds, my output will be stable. So you end up trying to answer the following question: what's the longest path, time-wise, from any input to any output? So you look at each of your inputs, well, what things does that affect? Well, it depends on your circuit, right? Maybe if it changes to a 1, it goes to the input of an OR gate, but another input's already 1, so that doesn't have any effect. Right, so this is done by exhaustive computer analysis. And the best you can hope to come up with is a worst case number. What's the maximum possible time from any input to any output? And if you find there's one path going from here to here with a propagation delay of 85 nanoseconds, you've got to assume that might be how long it takes an input to get to an output. And so that's going to affect how fast we can run our circuits, basically. So we'll loop back to that in a few minutes.
Is the reason that you type those things into your terminal and show on the screen so you can get like timings on the YouTube videos?
Oh yeah, yeah. Yeah, so
time when you type it in.
yeah, so I have a little window over here that I can type into, and it will record the timestamp of whatever I typed, and it's synchronized to the video recording, and then when I'm done, it takes all of those timestamps, puts them on the clipboard, so when I upload to YouTube, I go into the comments, I just hit a Control-V, and it pastes those timestamps. And if I'm
looking at those timestamps, I was like, is it manual going through these 2-hour videos?
yeah, it's nuts. It's very easy for me, and while I'm lecturing, I can just type, Control-Alt-N and say other questions, and so it pops up here, and now there's a timestamp for that. And then all those timestamps get written to the bottom of a file, which automatically gets pushed up to the web, so you can go to that timestamp index and search by topics and go through, any of the videos from 2020, 2021. Except if they don't have audio, and then they're not worth as much. But yeah, so it's totally painless for me to do that. All right. So other questions? Any questions on the
Which
lab?
one of the homework are you grading?
I don't know. I'm probably gonna look at a few of them because it was short. I told you I wouldn't do the one with the XOR gate, so I'm not going to grade that one. But I'll probably eyeball the other ones and split the points among those. But I already looked at a handful of them. They look good. I mean, I think people are in good shape with those questions. So.
We're gonna talk about the midterm, possibly.
Yeah. Yeah. Let's talk about the midterm next. And any lab questions first?
I'm confused on how we did the full adder versus the full adder and half adder designs again. Like, do you remember when we first talked about the 2-bit adder and we did it in a little more complex way than the half adder and full adder? So I'm a little confused on how exactly we did it.
All right, cool. Yeah, so let's do that. So there's 3 ways to build a 2-bit adder. Okay, at least 3 ways. The first way is make yourself a truth table. And for each of your 16 combinations of, 4 bits, 2 2-bit numbers, write down what the 3 output bits should be. And just do what we do in 120. Write an equation for each of these and then start pulling parts out of your bin and putting them together on a breadboard. And make a big, huge circuit. Okay? That's one approach. Which you need to do up to a point in the lab, right? But you're not going to actually build that circuit. Okay, but this is approach 1. It's a combinational circuit. 2 bits for B, 2 bits for A, that's 4 bits of input, 16 rows, 3 outputs, because you have a 3-bit sum, because your sum can be as high as 6, is 110. So that's one approach, but the equations end up really complex. So the second approach is to use this idea of a full adder. And so a full adder does 1 column of pencil and paper addition. So if you're adding numbers on paper, 0 plus 1 is 1, 1 plus 1 is 0, carry the 1, 1 plus 1 plus 1 is 1, carry the 1, right? So that part of the addition, that's what a single full adder will do. It will take an incoming carry and 2 bits of numbers that we want to add. It will tell us what their sum is and what the outgoing carry is. Okay, that's all there is to a full adder. It's basically adding 3 bits and generating a 2-bit sum. But we think of it as, we've got 2 bits coming in, let me call them A and B, and we have a possible carry coming in, which I'll call C in, and we generate a sum bit, which I'll call S, and we have a carry which might go into the next stage, so I'll call that C out. And this is a much simpler circuit than this. This is a circuit with just 3 inputs and 2 outputs, a carry out and a sum. So 8 rows, 2 outputs, and these equations actually boil down pretty nicely. So the second way we can build a 2-bit adder is to take 2 of these things and just hook them together. Take a full adder here and take the output and put that next to another full adder. So there's our carry in, there's our sum, there's our carry out, there's A and B. But what we do is we feed the low bits A0, B0 into here, the high bits A1, B1 into here. If the sum of these generates a carry, we take that carry and we feed it to the carry in of this next stage. And so we call this sum 0, we call this sum 1, and this final carry we get out, we call that sum 2. So if you have a pair of full adders, just hook them together like this and you've got a 2-bit adder. And if you want,
Can you do this for the n number of bits, right?
You can do this for any number of bits. You could make a 64-bit adder by running 64 of these together side by side. It's not a good adder, but it will work. It will add.
Is this not how it will be implemented in some, say, like a professional circuit, like a chip?
So this is not what you would do in a chip. Let's come back to that in a second. Let's finish this this branch of the story, and then let's talk about that, because that's a chapter 9 topic we'll come to. So this will give you a 2-bit adder, a pair of full adders, right? So you make the truth table for a full adder. You come up with the equations. You minimize them, and if you make 2 of those, you can hook them together. But we can make our life a little bit easier. So this is the second approach, right? A pair of full adders. The slightly easier way, though, is when we're adding our numbers together, we don't know when we're going to get a carry out, right? If I decided to add, you know, these two numbers together, 1 and 1 is 0, I've got a carry right there. And 1 plus 1 plus 0 is 0 with a carry of 1. So my sum would be 1, 0, 0. And I don't know when I'm going to have these carries, but what I do know is I never have a carry coming into this first stage. Because these are the first numbers I'm adding together, so I can't have a carry from the previous numbers to you know, carry into here. So this is always going to be a 0. So on this rightmost full adder, I don't need that carry input. I know this is always a 0. So I can replace this with an even simpler circuit, which we call a half adder. And a half adder looks just like a full adder, but there's no carry in. It just takes in 2 bits, A and B, it produces a sum, and it produces a carry out. And so the third and simplest way to make our 2-bit adder is to take a half adder and take a full adder and connect those together. And so here's your sum. And a half adder is a really, really simple circuit to build. If you make the truth table for it, it's I think it's 2 logic gates. So we make our simple half adder, our slightly more complex full adder. We connect the carry out from this to the carry in there, and then it's just hooking up your switches here, your LEDs there, or your output to your 7-segment decoder. And that's the third way to do it, and that's the way you want to tackle in Tinkercad, because, you know, fewer chips, easier to build, less chance of mistakes. Does that make sense?
Oh, sorry.
No, go ahead.
Could I ask a quick question?
Yeah, definitely.
So in Tinkercad, I see there's a 4-bit adder. So would we use 2 of those chips?
No, you have to make this yourself.
Oh, okay.
So you're making this out of ANDs, ORs, NANDs, NORs, NOTs, XORs, XNORs.
Okay, cool.
Yeah. All right, let's take a quick look at what happens if we try to make a 64-bit adder out of this. So each of these is a full adder. And this is just mimicking pencil and paper addition. So suppose we have pencil and paper addition and we've got, I'll just do a 16-bit number. Suppose I'm adding these two numbers together. Well, first I'm going to add 1 and 1. I'm going to get a 0 with a carry of 1. I'll add 1, 1, 0. I'll get a 0 with a carry of 1. I'll add 1, 1, 0. I get a 0 with a carry of 1. And you can see what's happening. Eventually I'll add 1, 1, and 0. I'll get a 0 with a carry of 1. And if these are zeros, then I'll get a 1 coming out here on the end. This first carry that I generated caused a carry to occur when I added these, and that carry caused a carry out of that stage and into the next stage. And so if you look at these carry outs, the effect is that this first carry is rippling down this whole chain, and the input of a 1 here will eventually cause an output of 1 here, and so on. So timing, right? Propagation delay. So if your full adder has, I don't know, let's say 4 levels of logic inside, and it takes 15 nanoseconds, let's say that's 60 nanoseconds from input to output. Well, until I've generated the correct carry here, this can't generate its correct result. it might add these numbers together and get an answer, but after 60 nanoseconds, this is going to suddenly change from a 0 to a 1, and now the circuitry has to respond to that. And that's going to be another 60 nanoseconds, after which we'll get a 1 out here, and so on. So if I have 16 stages, right, that's 16 times 60 nanoseconds. That's 100, that's like 1,000 nanoseconds. So that's a microsecond, which is a huge time to a computer. So in a lab, if we were just using switches to set inputs and see the output on LEDs, this would be fine. In a computer circuit, this would be really slow because now we have a potential longest path of a microsecond. Well, that means we can't run instructions faster than 1,000,000 times a second, and our clock speed just went down really low. So there's other ways we can do this adding. We can make something called a carry look-ahead adder, which is a really clever circuit that circumvents this problem. And if we have time in the course, when we get done with state machines and Verilog, we'll loop back to chapter 9, and typically we talk about things like carry look-ahead adders and Wallace trees for fast multiplication, and so on and so forth. If we don't get to that, you'll get some of that in a computer architecture class. And if you're electrical engineering or computer engineering, you'll definitely get to it in other EE courses.
Will we get to that in like 270?
Sometimes I talk about it in 270. It kind of depends how the class is going. It is a suitable topic for a microprocessor class though in 270. And it's interesting. A lot of work has been done in doing fast arithmetic. I mean, it's such a basic thing: add, subtract, multiply, divide, right? Well, if your adder is slow, your multiplier is going to be slow, because what is multiplication? It's repeated addition, add and shift. And so a lot of fast computation really boils down to how quickly can you add. And it's such a fundamental operation, right? And how quickly can you subtract? And if you're doing division, you definitely got to do subtraction. And we'll come back and we'll look at a subtraction circuit to go along with our addition circuit. And it turns out to be, if we know 2's complement, really easy to take an adder and turn it into a subtractor. So we'll come back to that another time. All right, good. Let's go ahead and talk about the midterm. So I posted a bit of a topic list, and this is not really specific to the exam that I'm writing. This is really just kind of a synopsis of what we've been talking about so far. So there's no real surprises in here, but some things that you should probably refresh yourself on. So right, this is a digital logic course, so ones and zeros, right? Everything is discrete, high or low, on or off, true or false, as opposed to what we do in 120, where we have circuits with voltages and currents that could be pretty much anything. It could be 1.5 volts coming out here, and so on. So we're interested in digital stuff. I'm not going to ask you on the exam about how transistors work, this idea of switches that can be turned on and off electrically, but we did talk about that a little bit, and that's just good to know in general, but that's not on the exam. Definitely binary numbers, so being able to take an integer, for example, and write it in binary. Being able to take negative numbers and write them in binary using 2's complement. I don't think I mentioned decimal numbers on here, but decimal numbers also. So 2.6, how do you write that in binary? So you just still weighted positional notation, but on the other side of the decimal point. So 2's complement, signed magnitude, which is the idea of instead of doing 2's complement, we'll just use a bit to say plus or minus. So if you can write 17, we could write minus 17 by just changing one bit to say this is a negative 17. We don't usually do that. We pretty much always use 2's complement for the stuff we do in this course, at least. And the range of numbers, right? If you have 4 bits, how many things can we represent? 2 to the 4th, 16. If we're representing non-negative integers, that means we could represent numbers from 0 to 15. If we want to allow negative numbers, we go from typically negative 8 to positive 7. So there's always a range it can move around. And so converting between decimal, binary, hex, octal. And the hard part of this is going to and from decimal. If you have a number in binary and you want to write it in hex, that's pretty straightforward, right? Here's a binary number. If I want to write it in hex, just break it into chunks of 4. So that's a 3, that's a 7. You've got to know, how you represent 10 through 15. But this is the number 11, which is a B. This is the number 14, which is an E. But it's really just, you can visually eyeball your number and break it up. So, and if we have a number, say an octal, we can convert that to binary by just taking each digit and writing 3 bits. So 7 is 111, 3 is 011, 5 is 101. So the binary version would just be that. And if we wanted to convert that to octal, we break it up into 4s. That's an F, that's a 5, that's a 1. So those are pretty mechanical. Going from binary to decimal, right, you add up the powers of 2. Going from a decimal number to binary, that's where you have to divide and look at remainders and that whole little routine that we've talked about. Or do it by trial and error or something. We can represent characters in binary, so you don't need to memorize the ASCII code or anything like that. But, we can use patterns of bits to represent numbers, but we could use them to represent characters of the alphabet. We could use them to represent pictures or movies or sounds or anything that we want. It's really up to whatever mapping we decide on. So there is a mapping called ASCII, which maps patterns of 7 bits to different characters. But there are other mappings such as EBCDIC that used to be popular. And there's modern mappings like Unicode, which is 16, 24, 32 bits, but still just mapping bit patterns to characters. Binary arithmetic, so we can add column by column, pencil and paper addition. We can subtract the same way. It's a little harder because we have borrows instead of carries. But we can also do subtraction by adding negatives, as long as we have a way to represent negatives. And if we're using 2's complement notation, we can write a negative, right? So flip all the bits, add 1, that's the negative of whatever number you started with. And so if we want to calculate A minus B, we can calculate A plus negative B, right? So calculate negative B, toggle the bits and add 1, and then just add that to A. Other ways we can represent numbers in binary, binary coded decimal. So this is another approach. If I wanted to take the number 127 in decimal and write it in BCD, well, you write a 4-bit pattern for each digit. So the number 1 is this, the number 2 is this, the number 7 is this. So that would be the number 127 written in BCD. If it's going to be in binary, then it would be weighted positional notation. And gray code, the only thing you want to know about gray code, this is this idea of only changing 1 bit as you move from one position to the next. I'm not going to ask you about that, but that's the thing we do on K-maps. All right, question in chat. Yeah, let me talk about this too. What format will this be in, and how long do you have? So my plan is this will show up at 12 o'clock on Canvas, and it will look like a homework. Okay, it won't show up as a Canvas quiz. It will show up as an assignment, and it'll be called midterm. And it will be a PDF, and it will have a bunch of questions in it. And you do it like a homework, right? Basically, just write up the answers on paper, scan those, take pictures, however you're submitting your homeworks, and submit those as a PDF. So you don't need to print out the exam and write on it, right? Because not everybody has a printer. But just take it like a homework assignment. I strongly recommend, writing this up by hand instead of trying to do it by typesetting with Word or something. Because truth tables and circuit diagrams and things like that, they're much easier to draw with pencil and paper. And, take a picture with a phone or a scanner or something. However you've been doing your homework should work fine. I'm going to give you 60 minutes for the exam. I'm not going to put a deadline on it. So you'll be able to submit after the deadline, but it's going to cost you 10 points per minute. So don't submit it late. Okay, but you're going to have to keep track of time. I will be in Zoom for the duration of the exam, I hope. And if questions come up, you can ping me in Zoom, and I'll try to give you a reminder a few minutes before the deadline. But don't play the clock, right? Don't wait until the very last second and then try to submit with 15 seconds left. Because if it comes in 30 seconds late, you're down 10 points. If it comes in 5 minutes late, you're down 50 points. Okay? If you have extended time for the exam, then just take the extended time. Okay? Canvas is not going to close out the exam or lock out submissions. Yeah.
So that means it's gonna only be open from 12 to 1. Is that how it is, or is it an hour from when you start it?
It's going to open up at 12, and you're going to have to submit by 1. It'll be open beyond that, but like I say, if you turn it in at 1:10, you've got a 0. Because it's going to be 10 points per minute, so make sure you turn it in before 1 o'clock.
How many questions are they going to be?
I'm thinking probably about 7 questions. Some of them shorter, some of them longer. You're going to want to work fast. You're going to want to show me what you're doing, but you're going to want to pace yourself.
So are we going to be in class for it? Because it looks like it's during the class time.
It's during class time, 12 o'clock to 1 o'clock. I strongly recommend being in Zoom during that time so that if there's corrections, for example, if someone says, hey, question 3 is impossible, and I say, oh yeah, that should be a 0 instead of a 1, right? I'll announce that in Zoom. If you're not in Zoom, then you don't hear that.
What's the policy on notes?
You can use whatever notes you want. You can use your old labs, your old homeworks, any of that stuff, but no online resources. Okay, so you're not allowed to Google, you're not allowed to Wikipedia, you're not allowed to Chegg. But you can use your textbook, you can use your notes, and you've only got an hour, so you really don't want to, for example, start going through lecture videos and trying to find where I talked about two's complement, right? You really want to make sure you've got notes written in front of you that you can refer to quickly. So no online resources, but you can use your own notes, labs, homeworks. And I'll make an entry for the midterm on Canvas, and it'll have these details on it, reminding you that what you're allowed to use and not use, and so on and so forth. And I'll probably send out an announcement ahead of time because for some reason there's usually some number of students who think that they can do the midterm anytime during the day instead of from 12 o'clock to 1 o'clock, and so 4 o'clock in the afternoon I'll hear from a student saying, hey, I can't get to the exam. So I'll probably send out an announcement in the next few days and just sort of reiterate what we're talking about right now, just to make sure everybody's on the same page. All right, other questions about this? And your questions are helping me figure out what I need to mention in that announcement, so these are good.
Will this study guide be in Canvas?
It's on Canvas, yeah, I posted it yesterday.
Okay, sweet.
Is there probably going to be a circuit diagram question?
Almost certainly. So the questions will be very much like homework questions you've done or questions you've seen in lab. I'm probably not going to throw anything at you that's like, you know, totally out of left field.
Please tell me we don't have to do anything in Tinkercad.
There will not be any Tinkercad on there.
Thank you.
Yeah.
Thank you. I'll do the whole lab and then spend, 4 hours on Tinkercad.
Yeah, no, we don't want that. The biggest thing prep-wise, though, is, you've been turning in PDFs for your homework, which is great. Just make sure that process is pretty fluid for you. If you finish your exam, 5 minutes early, and you start trying to turn it into a PDF, but the process, sometimes works, sometimes doesn't, that's like not something you want to deal with. So if you've had any weird issues with making a PDF or getting a PDF to upload to Canvas, try to smooth that out ahead of time. And if you're not sure how, come by office or lab and we can work on it and figure out some tools or some procedure that'll work better. But I don't want you to have to spend time or mental energy worrying about the logistics of the exam. I want you to be able to spend the whole time, working on digital logic, basically.
Could you quickly remind us what completeness of NAND and NOR is?
Yeah.
I'm a little confused by that.
Yeah, we haven't gotten there yet, but basically the fact that you can build any circuit out of just NAND gates or out of just NOR gates.
Oh, right.
And so there was a homework question which said, rebuild the following circuit with just NOR gates. So that kind of thing. Okay, good. If for some reason you cannot get into Canvas or something like that, right? Again, I'm planning to be in Zoom during the exam time. The one disclaimer I'll tell you, which I mentioned the other day, is I'm getting my second COVID shot that morning. So if bad things happen, I may be zooming from my phone or something. So I may have less access than I would like, but we'll figure it out as we go. But I'll set the midterm up to open automatically at 12. So if you don't hear from me and so on, just hop onto Canvas, and at 12 o'clock you should be able to access the midterm. Just start doing it, submit a PDF, and if we have to figure out details after the fact, we can do that. Don't miss your midterm. It makes it really complex if we have to start thinking about makeups and things like that.
Just got my second. It hurts.
Oh, yeah. Wide range of reactions. My mom, she's almost 90. She got her second one. She said it was no big deal. And some of my friends were like, on their back for like 3 days afterwards. So I think it's kind of hit and miss. Hi, Mom. My mom listens to my recordings sometimes, so I can give her a shout out. All right, so continuing with topics. So definitely know how to wire up switches. Oh wow, that sounds harsh. Definitely know how to wire up switches and LEDs. You've been doing this in a bunch of different circuits now, and I've been pointing it out if they're not quite right. But people have nailed switches, which is fantastic. LEDs, right? Make sure you have that 1K resistor in series. you should know basic logic gates, and or, nor, XOR, XNOR, and so on. You've been using those, no big deal. Here's the main things we've been doing, right? Starting with a truth table or a description of a circuit to a truth table, and then going to equations, and then using that to build a circuit. Or starting with a circuit, analyzing it, writing equations, and then turning that into a truth table. So we've done both directions, right? We haven't really talked about theorem proving, but you know, you can basically make a truth table to see if one thing's equivalent to another. I'm not going to ask you to do that. Sum of products, product of sums, full and compact. So if I asked you to write a sum of products representation of an equation, right? You want to say something like, you know, F equals A bar B C, or B C bar, or A C, right? That's a sum of products. If I say you can use compact form, that's when you can say sum of, you know, minterms 3, comma 2, comma whatever this is, 6 or 5 or whatever, right? So that's the compact form, that's the full form. And generally, unless someone says to use compact form, use full form. But I'll try to be explicit. So sum of products, product of sums, they're the duals to each other. We've done a bunch of those in homeworks. You're doing them on labs and so on. So you should know those. When we write compact form, sometimes you see this. This plus MD with some numbers, those are the don't cares. In a truth table, the don't cares look like dashes. And those affect us when we try to minimize our circuit, right? So minimization, we can minimize algebraically. We haven't really done a lot of that, but you know, you can combine things and try to simplify like that. But the usual way we minimize a truth table is with a K-map. So, you know, make the 4x4 block if it's 4 inputs, or a 4x2 if it's 3 inputs. And you've done a bunch of K-maps, right? So I think people are good with doing those. But, you know, make sure you use that funky numbering for the bits on the side. So 0, 0, 0, 1, 1, 1, 1, 0, right? So that it's that gray code. Cover your ones, optionally cover your don't cares, don't cover the zeros. This is for sum of products. And use large rectangles, use as few rectangles as necessary. And you can wrap on the edges, top to bottom, left to right. And you can wrap all 4 corners into one big broken up square if you want. And then write down for sum of products the minterms corresponding to each rectangle. For a product of sums, you cover the zeros and you write max terms. So same thing, but kind of a dual. Completeness we just talked about. Other logic blocks, multiplexers, demultiplexers, our 7-segment decoder, priority encoders, right? So I'll probably ask you something about muxes or demuxes, but go back and look at the homework questions on those, and you should be fine. And then programmable logic, PALs, PLAs, and PROMs. And basically knowing, you know, what those are about, and be able to, you know, draw connections on a fuse map to implement circuitry. So I think that's sufficient for the midterm. I'm not going to do any of the stuff we've been doing this week. Nothing about flip-flops or sequential logic or things like that. Okay.
I don't know if you mentioned this or not, but did you say that we're gonna have a mux demux question or no?
Probably, yeah.
Okay.
All right, other questions about that?
I don't quite remember much about muxes, to be honest. Could you like remind me what those are again?
Yeah, so these are the things that take either a few inputs to many or many inputs to a few.
Oh, okay. That's
Um,
right.
Is that enough?
Um, I might just rewatch like the lecture. Was that last Thursday that you talked about that?
It's been a few times because there were some homework questions and so on and so forth.
Okay.
So here's a basic mux.
Quick question.
Yeah.
Is it going to be in like the homework format, do you think, or will it be different?
What do you mean by the homework format?
About the demux, the muxers. The question that was on the mux.
Oh, I don't know. I haven't written it yet.
Okay.
Do we get the answers next to them, like on the homework?
So, say again?
Do we get the answers next to the questions, like on the homework?
No.
Aw.
Yeah, I know. I'm just mean that way. So a multiplexer, right? You have, say, two inputs, and you have a select line, and the select line will choose which of these inputs goes to the output. So it's like a controllable switch. A demux, you could have an input and one of two outputs. And it controls which output that input is connected to. And so they're good for, steering logic around the inside of a CPU and so on. But they're also good, muxes in particular, because we can implement random logic with these, right? If we wanted something which outputted a certain value for a 0 and a different value for a 1, we can just hook those values up to the inputs, and that implements our truth table. And so that was kind of what was going on with that homework question.
Thank you.
Yeah, you're welcome. All right, so let's do a 5-minute break. We'll come back at 1:18, and we'll continue talking about state machine analysis. Alrighty. So, any other questions before we go on?
Is there partial credit if we show a lot of work but we get it wrong?
Absolutely. Yeah, I'm all about partial credit, so definitely show your work. And teachers always say this, and it doesn't feel like it means a lot, but try not to stress over this, right? I'm really intending this to be very similar to homework questions and lab questions. So if the homeworks and labs are making some sense to you, you should be fine. Just kind of want to see, you know, what you're doing, what you're able to do in a timed situation, working on your own with limited outside resources. So that's really all that the midterm is. And if you're not clear, you know, what's going on with the homework or something like that, come by office hours and let's review whatever might be confusing. All right. So continuing with state machine analysis. So I posted some homework for next week. And these are mostly just, you know, continuations of what we started on Tuesday. So let me pull this up. So there's a lot of words here, but the punchline is, right, this is state machine analysis. The problems are long, right? You definitely want to spend time on them, and even if you manage to, like, you know, get them done at the very last minute, if you're not able to take the time to really think about these and try different things, then you're not going to get as much benefit out of them. So try to set aside some time to work on these. It's 5 questions. The 5th one is a shorter one, but it's a little different from the others. But these 4 questions are basically, you know, taking a circuit diagram for a state machine and analyzing it using this kind of 5-step process that we went through. And so question 1, you know, is this circuit right here. It has 1 input, it has 1 output, and a D flip-flop. And for this one, I've outlined the steps that you might take. So for example, how many flip-flops are there? Well, there's 1. I'll give you the answer for that. If there's 1 flip-flop, there's 2 possible states. Right, and that's kind of given away because I left you 2 spots in the state assignment table. So you look at the 2 possible values of Q, 0, 1, and just pick a name for each state. You could call it S0, S1, you could call it A and B, whatever you want, right? It's just a name to use when we make our diagram. And then write equations for the flip-flop inputs. Well, there's 1 flip-flop, which is a D, so there's 1 input. So write an equation for D, which looks like it comes from an AND gate. Write an equation for the output Z, which looks like it's just Q. And then make a state transition table. So that's going to look something like this. Present state, and you can put down the name of that. And you can put down the corresponding value of Q, so that comes from your state assignment table. And then your input X. Well, you have 1 possible state and 1 possible input, so you got 4 combinations of those. So fill that part of your table in. And then write down your Z output. And you've got an equation for Z that you'll figure out up here, so just fill in Z. You've got an equation for D, so fill that in. And now think about what happens when the clock ticks. And this is how you get these next state columns. So you have a D flip-flop. If the D input is a 0, then the next value of Q is going to be 0. If the current value of D is 1, the next value of Q is going to be 1. So D flip-flop, Q just takes on whatever D is. So based on your values for D, you can figure out what the new values for Q are, and then again go to your state transition table and fill in the names of those. Now you got a table. The middle part is just kind of, you know, filler, but basically it tells you if you're in this state and your input is this, then this is your output, and here's your next state.
Quick question.
Yeah.
What does it mean by name? I don't remember right off the top of my head.
Just the state is determined by the values of Q, but if you have, you know, multiple flip-flops, then you know you have one state when this Q is 0 and the next one is 1 and so on and so forth. So we want to have a name for each possible state. So in the example we did, I called this state S0 when Q is a 0 and S1 when Q is a 1.
5, right?
This is homework 5, yeah.
Okay.
So this is just a name to correspond to these values of Q.
So we're giving, in that lower table, just the other ones random names as well.
The same names that you used here.
But that's a state name for Q, but an S name is something different.
That's also for Q. So if we find the new value of Q is 1, then put down the name for the state when Q equals 1.
So they're all the same names, it's just present state, name of present state, name of next state.
Yeah.
Okay.
We're gonna do one of these right after this, so I think that'll clarify it.
Okay, thank you.
All right. And then is it a Mealy machine or a Moore machine? If Z only depends on the state, it's a Moore machine. If Z depends on the state and the input, that's called a Mealy machine. And then sketch your state transition. Sketch a state transition diagram, that should say, not table. So that's a typo. All right, and then question 2, same thing, but a different configuration and 2 outputs. Question 3, you got 2 T flip-flops. Question 4, you got a pair of JKs. Let's do a JK problem presently. And then question 5, this is a question about how fast we can clock our circuitry. And let me give you the basic setup on that, and then let's... Suppose I have some flip-flops, and I have some logic, and my logic feeds back into my flip-flops, and it also generates some outputs, and it also gets some inputs. All right, that's our basic model of a state machine. And suppose our logic takes, 100 nanoseconds, worst case, from inputs to outputs. Okay. So once our clock ticks, our flip-flops will change value. These numbers may change. And 100 nanoseconds later, these outputs will be whatever they're supposed to be. 50 nanoseconds after the clock tick, this circuitry may still be working to stabilize. So these values could be totally bogus. But we know if we wait 100 nanoseconds, in this case, once these inputs have changed, we know the output's going to be rock solid. So let's suppose the clock ticks. And that's at time 0. All right, logic output is stable at 100 nanoseconds. All right, we're going to tick the clock again, and that's going to cause these flip-flops to change, right? And the way the flip-flops respond depends on what their inputs are, the D input, the J input, all that kind of stuff. And those inputs are coming from this combinational logic, which means the inputs to the flip-flops are not stable until 100 nanoseconds, because the inputs to the flip-flops are coming from this logic. All right, suppose the setup time on our flip-flops is 25 nanoseconds. So remember what setup time is. It says that if the clock is going to tick right here, 25 nanoseconds before, our input has to be stable. Right? We're not allowed to change the input right before the clock ticks. And if we're told our setup time is 25 nanoseconds, we have to have our input stable at least 25 nanoseconds before the clock can tick. So if our inputs are stable at 100 nanoseconds, Soonest we can tick the clock would be 125 nanoseconds. So the clock ticks, let's call that time 0. The soonest we can tick the clock again is 125 nanoseconds later. And that's a function of the time it takes to propagate through the logic and the setup time for the flip-flop. Now there's also a hold time. We know that once the clock ticks, we're not allowed to change these too soon. But the hold time is usually pretty small. Let's say it's 10 nanoseconds. And it's very unlikely that in only 10 nanoseconds, the changes on the outputs will filter through this logic, come back around and change the inputs. So usually we end up ignoring the hold time in this analysis. But the propagation time of the logic and the setup time for the memory definitely tells us how much time we need between clock ticks. And so if that minimum time is 125 nanoseconds, and let's say it ticks on the positive edge of the clock, that tells us this has to be at least 125 nanoseconds. If we tried to tick the clock sooner than that, a few things could happen. It could be that the logic hasn't stabilized yet. Or it could be that, the logic stabilized, but we just set the correct input on the flip-flop, and now we're ticking the clock, and we haven't waited for the setup time. And so your logic might end up doing the wrong thing. So this has got to be greater than or equal to 125 nanoseconds. And if it takes, that's an eighth of a microsecond, which is an 8/millionth of a second. And so if we have to wait an 8/millionth of a second to tick the clock, how many times can we tick the clock per second? 8 million ticks. So this is just frequency is the reciprocal of the period. This is what the period is. It's how long it takes from one clock tick to another. If we take the reciprocal of that, that gives us the frequency. So with this particular set of timing characteristics, the smallest period is 125 nanoseconds, the maximum clock is 8 megahertz.
Does this mean that, in, say, a computer, any circuit that uses the clock must be faster than however fast the clock ticks?
Definitely. Right? So if we had a piece of circuitry that needed, 500 nanoseconds, then when we did this calculation, we would have found that, the minimum period was 500 some nanoseconds. And that would cause our clock speed to be a maximum of, say, 1.5 megahertz, which would be a slow enough clock for that very slow piece of logic. So it's really the speed of the logic determines what the clock rate is. And if you wanted to bump up the clock rate, anything that isn't fast enough is potentially going to malfunction.
So where it says logic output stable and input FS state, those are like ratings. So say if you bought those chips off the shelf, they would be a rating for how fast they can operate before they notch, right?
Basically, yeah, but you have to do a little bit of work, right? So if you design your state machine and you come up with a combinational logic, right, you need to do an analysis and say, well, I got inverters that take 10 nanoseconds and I got an AND gate that takes 10 nanoseconds, and here's what the logic looks like okay, my whole block of logic needs 20 nanoseconds. Or it looks like this, it needs 40 nanoseconds, right? So it's a combination of the physical components themselves and what the actual logic diagram is, how you've actually hooked these things together. And this is something we can minimize for, right? When we minimize, we end up with fewer components. A lot of times we end up with a faster circuit because there's fewer levels of logic for your input to pass through. And if that's not fast enough, yeah, you can go out, you can spend more money, and you can get yourself some inverters that have, a 1 nanosecond propagation delay.
Or you can just like fabricate a circuit with a certain size, right?
Mm-hmm. Yep. Now, what actually happens, though, and this is really sneaky, is two different things. One, you build your circuit and you test it, and you say, hey, I can run this thing at 12 megahertz, right? And you get this other one, and you say, oh, I can only run this at 8 megahertz, right? And so you have a fast version and a slow version of your product, and you sell those for different amounts of money.
Silicon lottery.
Yeah. But hopefully the manufacturer has thoroughly tested it and knows that this is a 12 megahertz. But a lot of times you'll design for a certain clock speed, and you may find out that the way you built this, it only goes up to 90. It needs 110 nanoseconds, and so you just sell that as a lower speed device. And so this is your overclocking thing, right? Sometimes you get a 2.4 gigahertz CPU, but it actually will work at 2.6 gigahertz because it was a good batch of silicon, and so that one you may be able to overclock more successfully. All right, so that's all that this question is asking. So play around with this one. There's a sample propagation delay and setup and hold times, and then some other short answer questions. So mess around with those. They're fun to think about. All right, so let's do a large state machine example with a pair of JK flip-flops, because that's kind of the most complex space, and we've got 15 minutes, so let's see what kind of progress we can make. I'm feeling pencil right now, because things always go wrong when you do these things on the fly. So let's make a random circuit. And I can do my circuit in pen. So I'll make a pair of JK flip-flops. And as I mentioned in the homework, we usually don't show the clocks at all. I'll put the little symbol, to illustrate these are clock devices, but we usually don't draw the clock lines. And when you design a state machine, the clocks all get tied together, and they all synchronize at the same time. It's the biggest wire in your entire circuit. It's the most power-hungry part of your circuit. An old processor called the Alpha had this thing they called the foot-long hot dog. It was the clock line to all of the flip-flops, and supposedly if you stretched it out, it would be a foot long, even though it was inside a little chip. And it was like this Greco-Roman fractal kind of design to try to make sure that the clock signal got to all of the flip-flops at about the same time. So lots of intricate design details going on. So we don't bother showing the clock.
Ground plane?
Say again?
Like a giant ground plane or something?
Kind of like that, yeah, except that if it was actually like a ground plane, it would be really hard to change its value fast. Ground planes work well because you want ground not to change, and so you're actually making a capacitor out of that. But the clock is a trickier problem because it's changing very rapidly. So we'll ignore the clock. We just understand that everything gets clocked together. And I'm just going to kind of make some random circuitry here. So I'm going to feed this into the K input, and I'm going to send this into J. Actually, I'm going to send it into J down here. And I don't know, I'll take another input. Let's call this X0. Let's take X1 and feed that into J. And let's take this and this, and we'll NAND those because NANDs are always good, and put that there, and we'll have an output here, Z. Alright, so truly a randomish circuit. Alright, so step one, how many flip-flops we got? 2 flip-flops, 4 possible states. Let's make a state table. So our state is what's the value of this flip-flop and that flip-flop. Right? 2 flip-flops, 4 possible combinations of values. So really, each combination of Q1 and Q0 represents a different state of the system. The whole business of the state assignment table, though, is just, you know, instead of constantly saying Q1 equals 1, Q0 equals 0, we're just going to come up with a name for each of these 4 conditions. So I'm just going to be unimaginative and call these what I was calling them on Tuesday. But, you know, you can call them A, B, C, D, or, you know, whatever. So I'll just call them S with a subscript that shows the values of Q1 and Q0. Alright, so the next step is writing equations for the flip-flop inputs and for any outputs from the machine. So, let's do that down here. So, J0, well, that one's easy. That's just connected to X1, which is an input. What about K0?
It's the AND of Q0 and X0.
It's the AND of Q0 and X0. Good. Alright, J1 looks like it comes from up here, comes over here. That's just Q0 bar. K1 is coming from a NAND gate. Looks like one of those inputs is Q0 bar. And the other input is Q1. And those are NANDed. And since we have not a whole lot of time, I'm going to use De Morgan on this and rewrite this, because I don't want to have too many columns in my table. So I'm going to rewrite this using De Morgan and say it's the OR of the complements of these. So this is Q0 ORed with Q1 bar. And you don't have to do that. You can leave it like this and just, you know, we're just going to use these to fill in our state table, basically. But this will save us a little bit of time. And then Z, which is the output from the circuit, is Q0 ANDed with X0. And it's going to be exactly the same thing as K0. Alright, we're done with our circuit diagram. Everything we need to know is in our equations. So let's go ahead and make our state table. So I'm going to list my present state, and I have I have 2 inputs X. So I'm going to have my present state and X1 and X0. And you kind of have to think ahead a little to know how to lay this out. But X0 and X1 can have any of 4 combinations. Did I really do this to myself? Wow. This is a much longer problem. Okay, well, let's start it anyway. All right, so we could be in state S00 or state S01 or state S10 or state 11. And those are just the names we're going to use when we make our final state diagram, but let's list the values of Q corresponding to those. So state S00, that's where both of our flip-flops have a value of 0. This next block is where our first flip-flop has a value of 0, but our second has a value of 1, and so on. Alright, so we got 16 possibilities of state and input. So let's list our output at this point, Z. So C is Q0 ANDed with X0. So Q0 ANDed with X0 can be a 1 here and here, and here and here, and it's going to be 0 everywhere else. And now we want to figure out what the new state is going to be. In other words, what's the new value of Q1 and the new value of Q0. So we want to fill in next state Q1 and Q0. And sometimes you see these with a little plus symbol on top to mean next state. So once we know the new value of Q1 and Q0, we know what the next state is. If the new value of Q1 is 1 and Q0 is 1, then our new state is S11. So the whole trick is figuring out what goes in these columns. And the only way we know what goes in those columns is by looking at the inputs to the flip-flops. So Q1 is a JK flip-flop. If we know the values of J1 and K1, we can figure out the new value of Q1. So we got to keep filling in from equations. J1 is the opposite of Q0. So this is going to be 1 1 1 1 0 0 0 0 1 1 1 1 0 0 0 0. And then K1 is this OR of Q0 with Q1 bar. So if Q1 is 0, this will definitely be a 1. And if Q0 is 1, this will be a 1. Alright, this is why we spend, 4 weeks of the course doing truth tables and equations and things like that. Because you use that to do this kind of analysis. Alright, so now you look at the behavior of a JK flip-flop. And in all 4 of these cases, J is 1 and K is 1. So what does the JK flip-flop do when both inputs are 1?
It's the same as the previous?
Almost.
Inverse?
It's the inverse. So if the inputs are 0, then it's the same as the previous. If both inputs are 1, it's the inverse. So in these first 4 cases, Q1 should toggle. So whatever Q1 is in the present state, it should have the opposite value in the next state. So all of these zeros are going to go to 1s. If J is a 0 and K is a 1, the new value of Q is going to be 0. So these will all be zeros. If J is a 1 and K is a 0, the new value will be 1. And there's another set of 0, 1s, the new value will be 0. So we know the new value of Q1. Do the same thing for flip-flop 0. So make a column for J0, K0, fill those in from your equations. Well, this isn't too bad, right? J0 is just x1. So 0, 0, 1, 1. Repeating pattern. You get really good at finding patterns, and it's really easy to make mistakes. And this is where, you know, having your work really helps, because the final diagram might be way off, and it might be because, you know, you wrote a 0 instead of a 1, right? I'm not worried about that kind of mistake. That's really easy to do. So if you show your work, I can say, oh, that's what went wrong, but everything else was fine. So that's good. All right, K0 is an AND between Q0 and X0, so these two columns right here. So these are all going to be zeros, and this will be a 1, and this will be a 1, but those will be zeros. These will all be zeros because Q0 is a 0. And then same pattern, this will be a 1 and a 1, those will be zeros. Alright, now using what we know about JK flip-flops, we can fill in the new value of Q. So 0, 0, Q0 should not change. It's a 0 in the present state, it'll be a 0 in the next state. 0 in the present state, 0 in the next state. A 1, 0 says the new value will be 1, so those are 1s. Here our inputs are 0, 0, 0, 0, the next state's the same as the present state. Well, the present state of 0 is a 1, so the next state will be a 1. And sometimes it's easier to do these by groupings, right? So anywhere I have a 0, 0, my new Q0 should be the same as the old. So this will be a 0, this will be a 0, and this one will be a 1. All right, anywhere there's a 0, 1, the new value is going to be 0. Anywhere there's a 1, 0, the new value will be a 1. And when J and K are both 1, Q should toggle. So here's a pair of 1s. The current value of Q is a 1. The new value will be 0. Current value is 0. New value will be 1. Current value is 1. New value will be 0.
You just toggled it when it was a 1, 0.
Which one? How far up from the bottom?
5 up.
This one?
Yeah, JK is 1, 0.
Alright. So 1, 0, alright, so it doesn't toggle, but it does set it because that's what a 1, 0 tells it to do. But yeah, it's not a toggle, you're right, thanks.
Oh, what's yours still on?
But it still works. Sometimes it works out. Alright, so let me put in the name of the next state, which is S10, S11, S01. There's your state transition diagram. I mean, your state transition table. How do we make a diagram out of that? Well, the other thing about your circuit is C of Z is a function of just the state or the state and the inputs. And if you look at the equation, Z depends not only on the state but also the inputs. So this is a Mealy machine, right? So a Mealy machine, we're going to draw like this. We're going to show the state. We're going to show transition arrows. And on those transition arrows, we're going to list the inputs, x1, x0, a slash, and then the output, Z in this case. And we have to show the outputs on these arrows because they depend on the inputs. If they only depended on state, we could just list the output as part of the state circle. So we could say state slash Z. Alright, we don't have time to draw this, but I'll do the first one or two. So there's 4 states. Let's look at the first row. If you're in state 0 and your inputs are 0, 0, you should go to state 1, 0. So we have a transition over to here if our inputs are 0, 0. And in that case, our output is a 0. If you're in 0, 0 and your input is 0, 1, we also go to state 1, 0. So here's another transition. That's for 0, 1, and our output is a 0. If we're in 0, 0 and our input is 1, 0, we're going to go to state 1, 1. So we'll have a transition like this. And that's for an input of 1, 0, and our output is a 0. And last one of this block, if you're in 0, 0 and your inputs are both 1s, you go to state 1, 1, and your output is a 0. So here's a transition. Input is 1, 1, output is 0. And you have to do that 12 more times, and you end up with a big horrible diagram, or maybe a beautiful diagram, or maybe both.
So, really quick.
Yeah.
I have a question. So it seems like every time you do a diagram like this, there's kind of an order of operations for how you analyze the circuit. And it seems like you first declare the states. So there were 4 in this one, S00, S01, S10, and S11, right?
Mm-hmm.
And then after that, you need to analyze what are the external inputs along with each state, and then the outputs of the entire thing, so Z. And then you start moving to like the internal inputs, which are like J0, K0, J1, K1, right?
Yeah, you're trying to write equations for the flip-flop inputs and for the circuit output.
Okay.
The right-hand side of those equations will involve, your external inputs, X0, X1, and your Qs and Q bars.
Okay.
But the equations describe the flip-flop inputs and the final outputs.
All right. And then after we have all that, we then analyze what the next states.
Then you go to the state transition table.
Okay.
And then after you've done the table, then you go ahead and you sketch a diagram. And that's sort of the final analysis of the circuit.
How do you know if it's a Mealy versus a Moore machine again?
So a Mealy machine, the outputs depend also on the inputs as well as the state. So if your output equations, if any of those output equations involve any of these inputs, then it's a Mealy machine. If they only involve the state, Q0, Q1 bar, things like that, then it's a Moore machine.
Okay, so just inside inputs for Moore machines.
Yes, yes.
Okay.
And a Mealy involves outside inputs. All right, that's a start to finish example, and we still have sound going, so that's good. So hopefully that's enough to let you make some good progress on the state machines. I have office hours tomorrow morning at 8:45, so I would suggest trying one of these. Maybe try that first one from the homework, so that you can catch me in office if you have questions about the procedure, and then you can potentially work on this over the weekend. Otherwise, you'd have to wait till Monday morning, and it's due Wednesday, so that's the suggestion. All right, thanks for sticking around the extra minutes. Have a good rest of the day, and I will see you next time.